In this activity, you will investigate the properties of the complex number z equals e to the I times pi over 3. Number 1, write z in Cartesian form, that is as x plus iy. Okay, so what we'll do is start with e to the I times pi over 3. We'll use Euler's formula to recognize that this is the same as, just write cis pi over 3. And that really means cosine of pi over 3 plus I times the sine of pi over 3. And that's equal to, and so cosine of pi over 3 is a half, plus I times the sine of pi over 3 is root 3 over 2. 2, for the complex numbers 1, 4, and root 13 e to the 0.8046i, write each number in Cartesian form. Okay, so this is the same idea as before. First two are easy. Cartesian form for 1 is just 1 plus I times 0. Cartesian form for 4 is the same thing, 4 plus I times 0. But the last one requires some work. This guy is equal to root 13 cis of 0.8046. So that's the same as the previous problem, just we have a root 13 in the front instead of a 1, which we had in the front on the previous one. So this is root 13 cosine of 0.8046 plus I sine of 0.8046. And so let's type this on the calculator. We'll go ahead and distribute the root 13 right now. So root 13 cosine 0.8046. It should be in radian mode unless there's degrees, and the calculator is in radian mode. So that's about 2.5. And then we'll do the same thing, but change this guy to sine. And we get about 2.6. So that's about equal to 2.5 plus I times 2.6. B, plot the numbers on the complex plane pictured. All right, so the first one we'll do in blue, 1 plus I times 0. So we go 1 to the right and 0 up or down. Next one is 4 plus I times 0, 4 to the right and 0 up or down. And the last one, 2.5 to the right, and then about 2.6 up, so somewhere around here. Find the product of each number with e to the I times pi over 3 and write the products in Cartesian form. Okay, so we want Cartesian form, so it seems like maybe we should, so we could start in Cartesian form. So the first one was just the number 1, right? Okay, so the first one is 1 times e to the I times pi over 3, and that's just e to the I times pi over 3. I'll just change this to blue so it matches the color that we had on the previous page. So this is just e to the I times pi over 3, and we want this in Cartesian form, so we've done this already. It's still a half plus root 3 over 2 times I. Okay, the next one was in green, 4 times e to the I pi over 3 is equal to, okay, so we're just doing 4 times, and then we'll go ahead and write our number in Cartesian form. So it's 4 times a half plus I root 3 over 2. Distributing the 4 gives 2 plus I times 2 root 3. And then finally, the last one in purple was root 13 times e to the 0.8046i, and that's getting multiplied by this new thing, the e to the I times pi over 3. Okay, so there's an easy way and a hard way, and they'll both work, but I'd like us to recognize the easy way. So what you could do is write this guy in Cartesian form, which we did on the previous page. you could write this guy in Cartesian form, which we did on the previous page, and then you can FOIL the two things together and you'll have your answer. Another option, however, is to recognize that, that we can multiply, for example, e to the a by e to the b, and we know in this case we're supposed to keep the base and add those powers. And so I'm going to do it this way. And it should give us the same answer. You might try the FOILing way too, but I think this will be a little bit more efficient. Root 13 is just hanging out waiting for us to deal with this guy. So this is really e to the I times 0.8046 plus pi over 3. So that's using our property up there in black. Equals root 13, and then we just need to do, we'll add these two guys up and get a single decimal. 0.8046 plus pi over 3. 1.8518. Okay, that's fine. And then that guy becomes root 13 times cis of 1.8518. And then we know that's cosine plus I sine, so let's do that calculation here. I'm going to store this guy as x because I'm going to use it a couple of times. So what we need is root 13 cosine of x. And then the same thing, root 13 sine of x. Okay, so this is darn close to the number -1 plus 3.464 pi. So that's it. And again, I recommend that you try rewriting each of these in Cartesian form and then foiling and make sure you get exactly that. Plot the products on the complex plane pictured. All right, so we'll keep our colors. So the first one is 1/2 plus I root 3 over 2. So root 3 over 2 you should type into the calculator. You get about 0.866. So we go 1/2 to the right and about 0.86 up, and we land somewhere around there. Next one is in green. 2 to the right and then 2 root 3 up. All right, so 2 root 3 I don't happen to know. 3.464, that's interesting. It's the same number that we had up above. Okay, so we're going 2 to the right and then 3.46, 3.5 up. So 2 to the right and then 3.5 up, somewhere around here. And the last one was 1 to the left and then 3.464 up. So the same height as this previous point. There. Okay, next one, 3. For the complex numbers 1 plus I, 3 plus I, 1 plus 3I, and 3 plus 3I, plot the numbers on the complex plane pictured. Okay, so let's try this. So 1 plus I, that means go 1 to the right and 1 up. I'm going to write this a bit to the left. 1 plus I is there. And then 3 plus I, 3 to the right and 1 up. And then 1 plus 3I, 1 right and 3 up. And then finally 3 plus 3I, 3 right, 3 up. Okay, so there's a square. Write each number in polar form as re to the I theta. Okay, so here we're going the other direction. And so we need to know the r and we need to know the theta in order to convert here. Okay, so in order to find, I'm going to do some of this work up here. In order to find the r, we got our fancy formula. It's just the square root of x squared plus y squared. So for example, for the first one, x and y are both 1. I'm looking at this black point right here, right? The coordinates there are 1 and 1. So this is just the square root of 1 squared plus 1 squared, square root of 1 plus 1, square root of 2. Okay, that's fine. And then the theta, well, the theta should be easy just by looking at that point, but in general, you're going to have to use this formula. It's the inverse tan of the y coordinate divided by the x coordinate. The y and x are both 1. And inverse tan of 1, you can type on the calculator, but I'm really hoping we can tell what this angle is right in here. That's 45. So I'll write that as pi over 4. Okay, so that means that the first point, 1 plus I, is really equal to re to the I theta, root 2 e to the I times pi over 4. Okay, and then the other parts are exactly the same as this, so I'm not going to show all the work. I'll just write these answers down here. But the next one was the green, 1 plus 3i. Actually, I'll do this in order. So the next one was blue, 3 plus I. So if you find the r value, you get root 10. And the theta value by doing inverse tan of 1 over 3, the y coordinate over the x coordinate, it's about 0.322. Okay, next one in green, 1 plus 3i. So again, if you find the r, you'll get root 10, which makes sense actually, right? Because the distance from the pole to the blue point is the same as from the pole to the green point. So root 10 e, and then here we'll get the kind of complementary angle. So that's 1.249. And then there's an I up here. And then finally purple, 3 plus 3i. So here the radius is different, it's further away. Square root of 3 squared plus 3 squared, or square root of 18. You can simplify that if you wish. And then the angle is, again, pi over 4. 45-degree angle right there. Okay, part C. What we're going to do is find the product of each number with z, which is still e to the I times pi over 3. And we'll write all our products in Cartesian form. Okay, so let's start with the black one. So that was right here. So we're doing 1 plus I, which was root 2 times e to the I pi over 4. So 1 plus I times z, let's just write the e to the I pi over 3, is the same thing as root 2 e to the I pi over 4. That's the 1 plus I, getting multiplied by this new number e to the pi over 3. And the same idea as before, the root 2 can hang out in the front. You copy the e and you add those powers. So we can add these powers up here. Just like we did, where did we do it? Right here. We ended up adding up the two powers that were right next to each other. So this is e to the pi over 4 plus pi over 3 times I. Okay, so we can smush those two things together. Common denominator is 12. I think we get 7 pi over 12 times I. And then we're going to have to take that and bring it into Cartesian because that's the desired output for this problem. So this is a root 2 times cis of this new angle, 7 pi over 12. And so here we'll let the calculator do some of the grunt work for us. Okay, so we're doing root 2 on the outside times cosine of 7 pi over 12. And then the same thing, but sine. Okay, so those are our two numbers, negative 0.366 plus 1.366i. Okay, the other parts of this problem are all the same. So I'm not going to show all the work, but it's exactly that same calculation that we just did there in black. So the next one we'll do is the blue one, 3 plus I times e to the I pi over 3. So you'll get root 102 Root 102 is me copying the wrong answer from the answer key. That should just be root 10. And then times e to the, and then we're adding together the two angles, 0.322 and pi over 3. Convert that to a cosine plus I sine. Use your calculator, and if I did it right, then we'll get 0.633 plus 3.098 I. Okay, next one we'll do is the green one, which was 1 plus 3i times our friend e to the I pi over 3. So again, here we'll get a root 10. We're going to have to add these angles, so that's the 1.249 plus the same pi over 3, I on the outside. Change that to cis, use your calculator, negative 2.098 plus 2.366i. And the last one, purple, 3 plus 3i times e to the I pi over 3. So here radius was root 18. Add the angles. We've done this one before. Pi over 4 and pi over 3. Still 7 pi over 12. At some point, use your calculator. Minus 1.098 plus 4.098i. Okay, part D, plot the products on the complex plane. Okay, so let's go in order here. So starting with black, I'm looking at this one right here. Minus 0.36 plus 1.36i. So left and then up. So left a little bit, 0.36, and then up a little more than 1, somewhere around there. Okay, in blue, 0.6 to the right and 3 up. Maybe around there. Green, 2 left and 2.3 up. And then finally purple, 1 left and 4 up. Around there. And well, it still kind of looks like a square actually, but it's been rotated. I think the next question is going to ask us to make that assessment. Based on your answers to 2 and 3, how does multiplying by z transform a shape in the complex plane? This property is used extensively in computer graphics. All right, so let's go back. So here were our original points right there. So it used to be that the black point was right here, and the black point has now moved over to here. All right, let's see. I'm also going to think about the orientation here. Did these guys stay in the same order, or did the order change? So going counterclockwise here, we go black, blue, purple, and green. Black, blue, purple, and green. So they stayed in the same relative position, like relative order next to each other. So it sure feels like it's a rotation. Is it obvious by how much it rotated? Well, it turns out it rotated by exactly the pi over 3 that we started with. If you take a look at each of these points, you'll see that they're 60 degrees counterclockwise from the original point. All of those got rotated around the origin. Okay, number 5. If the nth power of a complex number z is equal to 1, then z is called an nth root of unity. Part A, verify that z equals I times pi over 3 is a 6th root of unity. Okay, so let's understand the definition. It says if we take the nth power of the number, we should get 1. So in this case, it's the 6th power of the number. So we're going to take e to the I times pi over 3. We're going to raise it to the 6th. And we're going to say, is this by some miracle equal to 1? If it is, then we have a 6th root of unity. Okay, let's give it a shot. E to the I times pi over 3 raised to the 6th. When you have a power to a power, you get to multiply those powers together. So that's e to the I times 6 pi over 3, which is just 2 pi. And e to the I times 2 pi is really cis of 2 pi with a 1 in the front. And that's really cosine of 2 pi plus I sine of 2 pi. Cosine of 2 pi is 1. Sine of 2 pi is 0. So indeed, we got 1, which means e to the I pi over 3 is a 6th root of unity. B. There are a total of 6 6th roots of unity. Find the other 5 and write them in both polar form and Cartesian form. Okay, so we did something like this in the video for this particular class. So it's the same technique here. We're going to try to find complex numbers that when you take the 6th power of them, you get 1. So what I did in the class video, and don't write this, was I started off by making a generic complex number called z and raising it to the 6th power and making it equal to 1. But z is already reserved in this problem for e to the I pi over 3. So I'm going to use w instead of z. So I'll just make that clear here, where w is a general complex number. Okay, so the technique here, this is the complete way. Remember in the class video, we did it 2 ways. One of them was easier but incomplete. The other was harder but complete. Okay, so we're going to rewrite w as r e to the I theta, a very generic complex number, and it's still being raised to the 6th. I'm also going to rewrite 1 as a complex number. 1 is really the same as 1 plus 0i. That's not the form that I want it to be in. I want it to look like re to the I theta. So in terms of the number 1, which I'll just do a real quick plot over here. So the number plain old 1 is sitting right here. So then the question is, what's the r, which is that length, and what's the theta, which is the angle that that green line is off of the x-axis, but it's right there on the x-axis. So how much is the r? Well, the r is 1, that's how far it is. And the theta, because we didn't move at all, is 0. So that means that for the number 1, I can really rewrite that as 1 times e to the I times 0. It's kind of a silly way to write it, but it makes it look like the thing on the left, which is what I want. I wanted both of them to look like re to the I theta. Okay, now we're going to take the 6 and bring it into both of the factors. So we go r to the 6th, e to the, and then we know that we get to multiply the powers. So this will become I times 6 theta equals 1 e to the I times 0. And now we're going to make some pieces equal to each other, so this equation will be true. So I'm going to make the stuff in the front of the I equal, and then I'm going to make, or in front of the e, I should have said, make the stuff in front of the e equal, and then make the stuff next to the I equal. Everything else is copied on one side of the equation and the other. The e is the same, the I is the same. All right, so our two new equations, r to the 6th equals 1, and 6 theta equals 0. Okay, r to the 6th equals 1, so we take the 6th power, 6th root of both sides, and the 6th root of 1 is just 1. You could also say it's -1. I'm just going to choose to keep it positive. And here you're going to solve for theta, but we got to recognize that the zero angle is not the only angle we could have picked way back here. I could have said that the green line segment was formed by rotating around, once completely. In which case I could have said this is really 2 pi, or I could have said this is 4 pi, or 6 pi, or -8 pi. And so I could have said anything of the form 0 plus 2 pi k, and that's really the moment when we have to put that in there. So when we solve for theta by dividing by 6, we divide the 0 by 6, well the 0 is irrelevant, so divide the 2 pi by 6, we get 2 pi k over 6, or just pi over 3k. Oh, and finally, we're back to the pi over 3 that we've been looking at this whole activity. Okay, so I'm going to make a little chart here, and the chart is going to have a k column and an r e to the I theta column. And then maybe we'll convert all of those guys into Cartesian, x plus iy. Okay, values of k. I'm going to start with 0, 1, 2, 3, 4, 5. How do I know to stop at 5? Well, there are six roots of unity. And we can plug in k equals 6, and we'll see that we're back to something we've seen before, but just trust me on this one for now. Okay, r e to the I theta. R is always 1. That's easy. E to the I theta. The thetas are given by pi over 3 times k. So 1 e to the I, when k is 0, pi over 3 times 0 is 0. So that's that. The next one, when k is 1, 1 e to the I times pi over 3, just a single pi over 3. Okay, next one, 1 e to the I times 2 pi over 3s. 1 e to the I times 3 pi over 3s, which you can reduce. 3 pi over 3 is just pi. 1 e to the I times 4 pi over 3. And finally, 1 e to the I times 5 pi over 3. If you went one more to k equals 6, you'd get 1 e to the I times 6 pi over 3. But 6 pi over 3 is really just 2 pi, and going around 2 pi is the same as going around 0. So that's why we're back around to a copy of something we've seen before. Okay, and then in terms of writing each of these in Cartesian form, well, the first one is just 1, so that's easy. But the other ones you, I think, want to do the cis theta. So this guy right here, this one right here should be cis of pi over 3. So cosine pi over 3 plus I sine of pi over 3, which we've done before. That's the z that we've been playing around with this whole time. So the z that we had from before was, what, 1/2 plus I times root 3 over 2. Okay, but then this next one is new. So again, we're going to do cis, but now 2 pi over 3. And if we do that, we get negative 1/2 plus I times root 3 over 2. And the next one, e to the I pi. So again, you're doing cis, although e to the I pi, we actually looked at that separately. That just turns into negative 1, but you can do the cis and you'll see that you get negative 1. Cis of 4 pi over 3 gives negative 1/2 minus I root 3 over 2. So same numbers all the way through. We're just looking for the signs, I guess. And then cis of 5 pi over 3, 1/2 minus I root 3 over 2. Okay, next one, part C. There are 5 fifth roots of unity. What are they? Leaving them in polar form is fine. So here it's the same idea, and in fact, you might be comfortable enough to just write the answers based on the answers that we got in here. But I'm going to go through the process just so we see it one more time. So here we want fifth roots of unity. So some number to the fifth is supposed to equal 1. Change that w to a generic number in polar form, changing the 1 into its polar form. Oops, lost the 5. 5 comes in, r to the fifth, e to the I times 5 theta. Again, we're going to make the stuff in the front of the e equal. And we're going to make the stuff next to the I equal. R to the fifth is 1, and 5 theta is 0. Take the fifth root of both sides here. Fifth root of 1 is still 1. This is the part where it's easy to forget to add the 2 pi k, but we need that. And then when you divide by 5, we get 2 pi over 5 times k. Okay. Okay, so we'll go ahead and make our chart here. First column is k. Second column, re to the I theta. 0, 1, 2, 3, and 4. There are 5 fifth roots of unity, so 0 to 4. The r's for all of these are 1. When k is 0, so now we're plugging in to find the theta from that equation. So if k is 0, we just get 1e to the I times 0, which is just 1. But then we get the other ones. So when k is 1, 1e to the I times 2 pi over 5. 1e to the I times 2 of these guys, so 4 pi over 5. 1e to the I times 3 of those guys, 6 pi over 5. And then finally 1e to the I times 4 of those, 8 pi over 5. So those are the 5 fifth roots of unity. You could convert them into Cartesian, but this problem does not require it. And that is that.